Okay, so we will be talking about mostly about calculus and derivatives, and eventually this will lead us into what's it called, gradient descent. And gradient descent is one of like this really great tool that we can use, and it's used not just for, we're going to use it for linear regression, and you'll see that in section 14 as you guys go through. But it's useful for a lot of machine learning algorithms in general, and basically it's the idea of us learning. So like we can use the idea of gradient descent, and we'll talk about more about what that is, but we can use it to basically iteratively get better and better, a better and better prediction model. And we can use that something called the cost function. So we'll get all right into this. So first of all, thumbs up, thumbs down if someone's, who's read, at least maybe skimmed section 14. So I have an idea, and no judgment. Okay, cool. So people, okay, so most people maybe at least skimmed through it. Maybe you just did a little bit, maybe you read the whole thing through and you feel like, oh, I got this, it's more like review. Awesome. So I am going to share my screen, which always takes me longer than it should. But I can never find the page I'm supposed to be sharing. Okay, so you guys can all see my screen right now. Okay, and I'll make this a little bit bigger too. Make it easier to see. Okay, and so we are going to talk about two different parts. I have this Colab right here, Colab notebook. So at this point, we've probably seen a few of them now. But in case of people who haven't seen this before, it's essentially like a Jupyter. It can run Jupyter notebooks in the cloud. It's from Google. It's kind of like Google, like a Google Doc, but for data science, for Jupyter notebooks. So just know I sent you the link. It should be allowed so you can edit it. That way, in case you guys want to, if you're asking a question, you can type directly in there and we can run it directly. Check that out. But anyway, so introduction to derivatives. That's what the first part of the section is. So hopefully people feel pretty good about derivatives in general. Just kind of quick show of hands, who's done some calculus before? Who's that? Okay, cool. So hopefully this is review. Let me know if this is like getting too like, oh, I've done this before. I don't need to talk about this too long. Okay. So a derivative really is a rate of change. And so the curriculum again goes through this whole process of like basically introducing what a derivative is, how rates of change happen and everything like that. And basically we can also go into like second derivatives and even, you know, third, fourth derivatives and stuff like that. Basically talking about rates of change kind of deal. So the first thing is, the simplest one is if we have a rate of change for a linear function. So I'm mostly just going to draw because I think that makes more sense in these cases. But we can always think of like a linear function. It's always just a line, right? So if I have like some function like this, okay, our rate of change actually is really simple then. All we have to basically say is like, well, how much has it been changing, right? And in this case, it changes by its slope. It's rise over run. And hopefully you guys have heard those terms before. Again, hopefully this is more like review than anything, but a rise over run, rise meaning that's how much it's gone up by, and it's run, how much it's gone off to. In this case, we go from left to right in the positive direction. And we can think of this like, okay, this point right here, we'll call that x1, y1. So this little sub indexes right there. And then we can talk about this point on the line as x2, y2. Okay, those are the coordinate points. So we can then think, okay, well, this right here and this point right here, we moved to the right, we ran by x2 minus x1. And then we rose by y2 minus y1. So we can kind of see it's like, okay, this is how much we went across, this is how much you rose by. And this is like the direct, you know, exactly what we're writing out, like y2 minus y1. It doesn't really matter where we go on this point, in this case for the line, because we're always going to be on that line, right? It's a nice consistent slope, right? Slope doesn't change. So you've probably seen this back, you know, in grade school at some point, like as M, right? Sometimes I'll write this as A, just because like it matches our B kind of formula. But we can also say, well, okay, this y2 minus y1 and this x2 minus x1, you've probably seen this delta. That's what we call it, delta. But it's the change of y2, or I'm sorry, change of y over the change of x. Okay. And what's nice about this is that for at least a line, for a linear function, a line, whether it's going up or down, this is always the same. No matter where you pick your 2 points, the slope is always going to be the same. Because even if you increase, y by a large amount, x is going to increase by the same amount too. So this is where we'll usually write this like this. Now, what we'll tend to do, and I'm just going to go and clear this off. All right, I'm going to write on my little new, this is the new thing that I'm doing. If I can click. Okay. Huh, that's funny. Okay, so we can also think of like when we have our function like this, we have our line, right? And then if we have our rise over run, our 2 points that we're comparing, right? Right here and right here. Okay. And I said this is like basically our delta y. And this is our delta x. Okay, our change in x. We can also write this, because remember this is just y2 minus, y2 minus y1. If we call this like this line, which is a function, if we just call it, oh, it is a function, f, okay, we can say, well, okay, we can say, okay, well, what is the value of y2? Well, y2 is just how tall it is, right? Which is literally the same thing as just saying f of x2, which is this point right here. So we basically input x2, we get our y, so we can just call this f of x2. And then very similarly, we can have this part right here. Well, we get this height, which is y1, right, is just f of x1. Okay, so we'll see it like this. All right, so this is, you'll usually see something along this lines, but you'll notice, for example, I have right here, you're like, what's this delta part? And basically it's a way to generalize a little bit more, so you don't have to think about the small, or you don't have to think about multiple points. We can just think, oh, we just increase it a little bit. So this can actually be written as f of x, meaning some point x, I'll just call this x right here, or I'll call this point x, plus some change in x, right? And you can see that that right there is this number, right? Because basically we say, okay, this part to this part right here, we're getting the full thing. We're saying, oh, if this is like x1 and we add on that little change in x, this is the same thing as x2. So that's why we're able to write that. And then of course we have minus f of x1. But usually since we're only talking about one little number, we'll get rid of that little notation underneath and we'll just call it x. Okay? And what's the beauty about this is that we can write our whole slope here, our whole change, as just in terms of x. Oops, I wrote that wrong. Sorry, guys. Whoa, that's not what I wanted. This is me erasing. Delta x, okay? Which again was just x2 minus x1. So we get this whole nice function going on here, okay? And that's what we actually call a derivative. Like, and well, that's not quite true. We'll do a little extra thing to get to a nice derivative, but essentially this will be the derivative for a linear function, is that change in x. So real quick, does it matter what the little delta is for a linear function? If I have a large delta or a small delta? Did I see some head shakes? No, it doesn't matter, right? Because the slope's the same every time. So I could have made like the delta like really, really small, like super small, or I could have made it like the whole, like this huge function, right? And that's delta x. Like, it doesn't really matter because the slope doesn't change. So linear functions are easy. Basically, you'll see like their rate of change, or what will be their derivative, will always be constant, which means the function looks like this, right? If I can draw straight lines, but I can't. But we'll call this f prime, okay? And note that derivatives, depending on who you talk to, they'll write derivatives differently. Some people like the notation like f prime like this. Also know that this is the same thing, we'll later find out, for a one function. You also see it like this with lowercase d's, okay? And these will mean the same thing for one-dimensional objects, or one-dimensional function, or not, that's not the right way. Yeah, we'll talk about that. When we start getting other variables in our function, we'll notice that it'll be an issue. We'll have to think about it a little differently. But anyway, we go from a line to basically a straight horizontal line, okay? So that kind of gives us an idea. So this is a number. This is actually something like a function of x, and it goes something like with x. There's no squares. There's no 1 over x's. There's no y's in there or anything weird. Just numbers in x, okay? Simple stuff. I think thumbs up if you felt good about that. Cool. All right. I always have to ask you guys and look over because you guys are so quiet. Any questions? Oh, someone asked something in chat. Okay, good, shit. All right, so easy, right? So next is gonna basically, we're gonna talk about nonlinear functions. And nonlinear functions, it's actually not that different from what we're gonna do, but there's a little twist to it. So we'll kind of clear this out, okay? And we have a nonlinear function, and there's actually a subtle point to this, is that the function actually has to be differentiable, which basically just means you can take a derivative. We can go in the whole mathematical formalism of what differential means, but we're not going to talk about that. But the main thing is that you have some nonlinear function like this, okay? Clearly that is not a line, right? So we can now still make our quote unquote our derivative part. So let's take from here to, let's say from here to here. So here's our change in x, and we can see our change in y. So we can remember our delta y, our delta x, okay? Or as we saw before, we can create that as our f x plus delta x minus f of x all over delta x, okay? And that basically is telling us is what is, let's say this is our point right here. Oops, I'm using the wrong tools, guys, sorry. So if let's say this is our x point right here, it is saying the slope at that point. So like basically how steep is it at the specific point? But you'll notice like, okay, it's kind of close, but you know, maybe my drawing's not great. But if you imagine instead, if we took the derivative, basically the rate of change at, let's say, I'm trying to find a good spot. Let's say like this point right here, okay? And I make I make my rate of change, or my delta x very large, and you can kind of see where that slope will end up being. That's not going to be exactly on the function. In fact, your derivative for nonlinear functions tends to never be on the function directly, just on that very small point. So the problem is that this is not going to be a very good estimation. But what could we do to make that estimation better? Yeah, I see Matt. So Matt basically went like this, like, oh, it's got to be small, right? And so we said, oh, well, instead of having this huge thing, because like, duh, that's kind of ridiculous, let's make it much smaller. We can make it smaller. And then of course we can make it smaller and smaller and smaller. And I know like physics, we love the word infinitesimal. You basically make it infinitely small. You make it as small as possible. And basically what that means, anyone know what that means when we say it's infinitely small, what we're doing to this function? Starts with an L. Taking that limit, delta x is approaching 0. We're making delta x really small. So you'll see this notation like this, the limit of delta x, or something equivalent like that, to approach to 0, and then of the whole derivative part. F of x plus delta x. Sorry if my writing's not the perfect. Of f minus f of x divided by delta x. Okay, and this is the derivative of f of x and f prime of x like this. Okay, and you'll see that in the curriculum. I'm gonna talk about that, and they'll show you kind of like how you could like show this points. But what's nice about this now is that when we have this tool right here, you know, there's kind of a little mathematical mess going on here, kind of a bit to go, you know, trying to figure this out. But if we could figure out what this stuff is over here, then we can just simply put in whatever number we want into the derivative, and we'll know instantly what that slope is on that exact point on the function. Okay, we could actually do this twice too. basically take a derivative of derivative, because basically the idea is like, well, if we take derivative here and it gives us a nice function, right? We can then take the derivative of that function. And so this is where, for example, second derivatives, we tend to focus on second derivatives. Like there's not too many cases when we'll start thinking about third and fourth derivatives, but it is technically possible as long as your function is differentiable. Okay. Any questions about any of this stuff right here? Okay, thumbs up. Hopefully this feels like pretty like review, like feels pretty easy. Okay. So again, all we're doing for derivatives is just literally the rate of change, how something changes. So we have a few rules. So we have the power rule, addition terms and coefficients. The curriculum kind of goes into a lot of detail about what this looks like, but I'll kind of just quickly, briefly talk about what those power rules are. So does anyone, well, let's see. If I have, let's say, my function of x, right, is equal to x to the power of some, I'll just put n. So some number, some integer, or not even an integer, but some number. Does anyone know what the derivative will be for this guy? Go ahead and unmute yourself and talk to me so I'm not like talking to myself.
It's n times x to the power of n minus 1.
Ah, very good. This is the power rule. And I swear my n's are better. And I see someone else did this on the chat. Perfect. Okay, yeah, John, yeah, you're right. John put 2 times x. So if it was x squared, it would be 2x, okay? So I'm trying to go back to clicking this. Okay, so this is the power rule. Note, however, there is a slight, doesn't always work. There's one case that doesn't work. Does anyone know when this power rule doesn't work?
We're using e or logarithm things?
Actually, I mean, as long as it's a constant, you know, like a number. So as long as it's n, this n could actually even be like 1.2. It could even be like pi. Okay, it doesn't really matter what the number is necessarily, but it just has to be that part. It actually, the time it doesn't work is when you have, let's see here, I think someone just said it in the chat. You're close, yeah. It actually does work for 0 if you think of it this way. I mean, let's try 0. So if we do, oops, let's try x to the power of 0. What is that number? Yeah, it's just 1, right? The derivative of 1 actually turns out to be just 0. And so it turns out, for example, if we do the power rule, we can do 0 times x to the power of minus 1. Well, 0 times anything, as long as it's not divided by 0, it's just 0. So it turns out it does work for 0. But you're close. The one, I always say the two parts that you can kind of reason for it is like, oh, is it 1 or 0? There's another one, x minus 1. X to the power of minus 1 is 1 over x. If you try taking the derivative of this one, did I have that right? Oh, I'm sorry. You know what, guys? Completely ignore me. It's been a long day, guys. I'm thinking of going the other direction when we're doing integrals. So ignore it. It does work for powers. Thank you, guys. You guys should catch me on this. You see? Keeping you guys on your toes. Okay. So anyway, the power rule, pretty much the most common one that we have. You can get other weird functions, which means you have to kind of figure out what those derivatives are. But the power rule tends to be pretty useful in the sense that it's what we mostly see. The curriculum just talks about this, is that if we have multiple, if our f of x is something like x cubed plus x squared, like plus x, all you have to do is just take the derivative of each one and add them together. Okay, so I'll put minus 1 up here. So this would be 3x squared for the power rule plus 2x plus, I'll put this here, minus 1 times x to the minus 2. Okay, so basically this is your derivative right here. This allows us to quickly take the terms and take the derivatives. And then if I just threw a coefficient here, put like times a, some number, this would just be 3a. Okay, now I'm going to go into details of that. So pretty simple. Those are the main rules that we'll use. Okay, any questions on this? Yeah, sorry for messing you guys up on that. That was my bad. All right. So the chain rule now, though. Okay, chain rule is actually not that bad in my opinion, but people kind of freak out about it sometimes. Basically, a chain rule says like, well, what if I have a function like this, where it's like a function within a function? And so you'll see something like if you have a composition, and I'm going to use G and H. So if we have something like G is a function and H is a function, like this, how do we find f prime of x? Okay. So an example of this would be if I had something like x cubed plus x squared, which we know how to take the derivative of now, right? That should be easy. But all of this is to the power of like, I don't know, let's say to the power of 2, okay? Now, what are some options we could do? Anyone got a guess? No takers? Okay. One thing, if you didn't know the chain rule, you could just square each part, right? You could try to basically say, oh, let me do x3 plus x2, and we would get this whole mess of x to the power of 6 plus 2x to the power of 5. And if I mess up, let me know, guys. Plus x to the power of 4. Right? Okay, we could have done that, and then we take the derivative of this, and then we get 6x to the power of 5 plus 10x to the power of 4 plus 4x to the power of 3. Okay, so we could have done all that stuff. I'm like, okay, that took a little long. The chain rule, if you had more complicated functions, especially like if you had something like, let's say a sine function, you know what the derivative of sine is, but like what's inside this, you can use the chain rule. So one way you can do the chain rule basically is you say, well, okay, let me take the derivative of what g is. So in this case, it would be, if you imagine, the way I like to say this is like, if you took instead, pretend this whole thing, we'll just call it like, I don't know, q. Okay. So if I did q, like the derivative of q squared with respect to q, it would just simply be 2 times q, right? Okay. So that seems pretty simple by itself. But we also need to take the derivative of the stuff inside here and multiply it. And that's really what the chain rule is. So instead of just having this q part, which q would be x cubed plus x cubed plus x squared, we also take the derivative of this part, which is just 3x squared plus 2x. Okay. And then this cube part right here, x cubed plus x squared. So the way you write this out usually is g prime of x times h of x. Oh, sorry, of h of x. Okay, makes sense. And again, curriculum goes through more. Any questions on this? I didn't do anything wrong on here, did I? Like if you see something that pops up, let me know. So I'm doing it all on the fly. Okay, cool. Simple enough. Chain rule, awesome. All right. So the reason why we do derivatives, partly is to find the rate of change, but also derivatives are really useful for finding minimum and maximums. Basically, we can start seeing when the rate of change changes. So for example, if I have, I'm going to clear off this part. I'm going to go back to my board over here. Oops. Of course. Okay. Go back to my board. If I have some function and the function kind of goes like this over time, I want to find when is it the smallest. Well, basically I can say, well, when does that rate of change go from positive to negative? Okay. And so we can actually use this part right here to figure out when this, when the minimum or maximum happens. And that's why derivatives are super useful when we're looking at something like we're trying to minimize or maximize. So later on, we'll talk about minimizing the error. We can use derivatives basically to find out when this part right here will actually end up being the minimum. Okay. Now the curriculum goes through a whole bunch of it, so I won't go into it unless you guys would like me to. But basically, you can think of it like when we take the derivative here. If you imagine this is more like a parabola, okay, your derivative will look like this. Okay, so it's basically the change is changing, if that makes sense. And then our second derivative, if you take a second derivative, you'd actually see that it would be a flat line. Okay, it's because our rate of change the rate of change of a rate of change does not change. It's a mouthful, but you can see this like, okay, this is change right here. And basically you can think of this, usually it's kind of like, not an inflection point, but basically when that rate of change changes. And that's what happens when we can find the minimum here. So we can use that with derivatives by basically observing the derivatives through here. That's how we found our min-max. Again, I'm not going to go into full detail of that because the curriculum does a great job just walking through that whole part and then showing you how to do the calculation part. Okay. But any questions on anything about derivatives right now? Cool. All right, thumbs up, you're feeling pretty good about derivatives. Okay. Yeah, if I gave you something to take a derivative of, you probably could find it. If you have something funky, you could do like what's called like sines and cosines and other crazy stuff. But honestly, most of the derivatives you kind of do in linear algebra tend to be power rules and stuff like that. Or you can make it into a power rule, which makes it a lot easier to solve. So just know that those exist. But yeah, okay.